Hello everyone. In lecture 4, I am going to discuss about the concept of stress and strain. The fundamental of concept of stress and strain can be understood by considering a prismatic bar. Considering a prismatic bar that is loaded by an axial force P. So, what is a prismatic bar? Prismatic bar is a structural member which has constant cross-sectional area throughout its length. What do you mean by cross-sectional area? If we are passing a section which is perpendicular to its longitudinal axis, then the area cut by this section is known as cross-section. It has the minimum amount of area when section is passing through the perpendicular to the longitudinal axis. Okay, so prismatic bar is a structural bar which has constant cross-sectional area throughout its length. Okay, so in order to investigate the internal stresses produced in the bar at any location, we have taken a section, imaginary section Mn at this particular location, and after that drawing free body diagram of this particular part. So free body diagram will be look like this is an axial force P and these are internal forces that is induced inside the material. But the thing is, the summation of all these forces will be exactly equal to P because this bar is in equilibrium. So the intensity of these internal forces, no doubt this will be exactly equal to P, and over cross-sectional area, means this is the area, is defined as stress and it is denoted by a Greek letter sigma. So if there is a pulling of the bar, the stresses generated inside the bar is called as tensile stress. But if the direction of the load is reversed, means there is a pushing of the bar, in that case the stress generated in the bar will be called as compressive stress. Okay. Here it must be noted that these internal forces that is generated inside the material, it is perpendicular to the cross section. So that's why all these stresses are called normal stresses. So normal stresses can be either a tensile stress or compressive stress depending upon the load acting, that is it is either of pulling in nature or pushing in nature. Clear? So here it must be noted that this stress computation, that is nothing but the internal forces per unit cross sectional area is the amount of stress, and this is the load acting, basically this is the summation over this cross sectional area. So it is a no doubt a statical parameter, means we have just considered the equation condition of equilibrium, means this external load P that will be exactly equal to the this summation of all these internal forces generated inside the material, and this is the geometric parameter. This is the geometric parameter. So the stress is totally only depends upon the statical parameter and geometrical parameter. and nothing else. So this formula is valid for all types of material. For example, if I ask, this is a material 1, say it is aluminum and this is steel, and load acting on both the material is same. No doubt this axial load is coinciding with its centroidal axis. In that situation, if cross sectional area is same, if cross sectional area here is also same, then what will be stress generated? So in both cases the stress generated will be P by A, it will be same, provided the load acting in both the cases will be along the centroidal axis. So the unit of load will be, what will be unit of stress? So unit of load will be Newton, and unit of, this is the cross sectional area, so unit will be, it will be meter square. So this will be unit of stress will be Newton per meter square, and this is known as, also known as, it is Pascal. So 1 Pascal equal to 1 Newton meter square. In fact, this 1 Newton per meter square is a very less quantity. Just you can imagine 1 psi equal to 7000 Pascal. So in practice, the higher unit for stress is used, such that just like megapascal, that will be equal to 10 to the power 6 Pascal, gigapascal, that will be 10 to the power 9 Pascal. Okay. Further, the next is when bar is loaded by an axial force, then what is the next observation is there will be the change in length. Let the change in length is delta. It must be noted here that this change in length is the cumulative result of stretching of the bar. Cumulative result means what? If this is the length L, then if I ask what will be the change in length there is change in length is delta. So for L by 2 the change in length will be delta by 2. So for unit length, what will be change in length? So this is 1 by L of delta, and this is known as strain. Means strain is nothing but change in length upon original length. But this formula for strain is, that is change in length per unit length, it is only valid if the material is homogeneous. Means this elongation will be uniformly distributed over this length. Then strain can be computed as change in length upon original length. Okay. So here we have seen that the formula for stress and strain, means formula for stress is P by A and formula for strain is change in length upon original length, is purely based upon statistical and geometrical consideration. So it is valid for all types of material, provided the principal requirement for validation of these two formula is, what is the principal requirement? First one is bar must be prismatic, If bar is prismatic, then only these formulas are valid. Second one is it is homogeneous, and third requirement is load must act through its centroidal axis. In that situation, all these both formula sigma equal to P by A and epsilon equal to delta by L will be valid. Next is, suppose if problem is like that, let's apply this particular concept on a particular problem. If there is a bar and load is acting is P, and someone say here a property known as Young's modulus of elasticity is varying from this location to this location, from E1 to E2 linearly, and it is increasing. Then what will be the value of stress at x equal to L by 2 if the length of the bar is L? Okay, so here we go for the formula for stress, that is equal to P by A. So while computing this formula, we have not mentioned any condition for the material to be isotropic or anisotropic. Only principal requirement is the bar must be prismatic, homogeneous, and load must act through its centroidal axis. So no doubt there is no confusion. Now whatever is the value of property, any property, Young's modulus or whatever, the stress at this particular location will be P by A. It only depends what is the load acting and what is the cross-sectional area. Next is, for same situation, it is the same bar and loaded by an axial force P. And if now we are interested to calculate the stress at some inclined plane, so how to compute the stress, the value of stress at this particular inclined plane? So again we are drawing the free body diagram of the any one part, either this part or this part. So if we are drawing free body diagram of this one, so this is load acting P. So internal forces will be here like this one. Okay, this bar is in equilibrium, so no doubt this bar, this particular half, this is the inclined plane at which we are interested to find the magnitude of stress. So again, from static condition, if this part is in equilibrium, then summation of all internal forces over this cross section will be exactly equal to P. So let I am representing it like this one. Let this is one is P, and here is given, let this angle is theta. Okay, so if this angle is theta, then if I taking normal to this plane, so this will be normal, and another component will be along the plane. Okay, so amount of this resultant is P, amount of these internal forces, resultant of these internal forces is P, and this angle is theta. So what will be the component of force in this direction, in normal direction? So this will be P cos theta, and along this plane will be P sin theta. Okay, no doubt this will make a parallelogram. Its diagonal represents its resultant amount. So due to this component, there will be a stress on this particular MN plane, which will produce, because this is perpendicular to this plane, it will produce a normal stress, and due to this component P sin theta, the internal stresses at this particular MN plane will be shear stress, because this component is acting along the plane. So how to compute normal stress on this particular plane? So value of normal stress will be the normal component of force divided by area of inclined plane. Similarly, what will be the value of shear stress along the plane? So tangential component of the force, that is P sin theta, tangential component upon area of inclined plane. Okay, if this area is A naught, then this area will be, this is A dash, so A dash will be A naught divided by cos theta. Cos theta equal to base upon hypotenuse, so A dash will be A naught by cos theta. So what will be sigma n? We get sigma n equal to normal component is P cos theta. P cos theta divided by A dash, that will be P cos square theta divided by A naught, and tangential component will be P sin theta is the tangential component, and divided by area of inclined plane, that is A dash, that is equal to A naught by cos theta. So this will be A naught divided by cos theta, so it will be A. So this is the magnitude of normal stress P cos square theta upon A naught. We have already seen this P upon A naught is nothing but stress in x direction. So this one is x direction. So this will be sigma x cos square theta, and this is nothing but sigma x sin theta cos theta. So we have determined the stress component at this particular inclined plane, that is normal stress and shear stress. The normal stress is sigma x cos square theta, and tau is sigma x sin theta cos theta. It must be noted here, the sigma and normal component of stress is a function of theta, and shear stress component is also a function of theta. So at different value of theta angle, all these components will change. So both these stresses depends on the angle theta. Okay, so if we plot all these stresses versus theta for minus 90 will be what? This location, this will be plane, to plus 90, this location. So stress distribution will be something like this. We are plotting for minus 90 degree to plus 90 degree. So we are taking, let's, here is minus 45 and here is plus 45 degree. So at minus degree, 90 degree, what will be the sigma n? So it will vanish as 0. It will also vanish as 0. So this is 0. Clear? At minus 45 degree, it gives sigma x by 2. Sigma x by 2, that is 0.5 sigma x. So this will be the location. This is the point. And if we plot sigma n, so at theta equal to 0, this is 0 degree. At theta equal to 0 degree, this will be sigma x. So double of this will be the sigma x. So sigma n plot will be something like this. It moves like, again at 45, it will gives sigma x by 2, 0.5 sigma x. So this will be the variation of normal stress from minus 90 degree to plus 90 degree. We are plotting here both sigma x value and sigma n value, normal stress and tau. If we are plotting tau, so at minus 90 degree it is 0, at minus 45 it will gives again 0.5x, but at 0 degree this will be sin 0 will be 0, so tau will be 0. So curve like this, there will be this variation. At minus s at plus 45, this will be, actually if we consider the positive sign, so according to sign convention, tau will be, this will be minus p, because if we are reference, so clockwise shear stress is produced positive, so here must be minus sign, and this is the positive normal stress outward, means acting perpendicular to the plane. So there will be, using sign convention, this will be minus. So at 45 degree it will give minus sigma by 2, 0.5 sigma x, and again at theta equal to 90 degree it will be 0. So this is the variation for tau, and this is variation for normal stress. So using condition of equilibrium, no doubt we can found the component, normal component of stress and tangential component of stress. Normal component of stress is known as normal stress, and this is tangential component is known as shear stress. Thank you.